Yeah, we're gonna do, I did this, visualization thingy, like here, and, we're gonna see if we can use it to make to visualize a neural net, isn't it? So, let me explain the visualization thingy, maybe? I gotta like get reoriented. No, just wait. Where is it? Oh, it's right here. Okay. Yeah. Okay. So yeah. This is I was just killing the bitrate of my video. Anyway, so what we're visualizing here is a single layer of a 4-bit neural net. So like it's taking on 4 bits, and then it has like four, units. So it's mapping like 4 bits to 4 bits, and this is the weights, right? So like each row of matrix A is also this is all implemented with ChatGPT. So just as an aside, so this is these are the rows. So you have like four units in the output, and each unit has one of these. These are weight arrays, and so each unit is computing thresholded Hamming distance, which is like whether the input unit is like close in Hamming distance to the parameter vector. And that's kind of like, dot product in, like a more traditional neural net with real values, floating values, whatever. It's just, it's like we don't have any BIOS, which limits us to like computing. It limits us in some way that I don't fully understand. It's something like it has to. It's symmetric under negation, or like it's like if you negate the input, it always flips the output bit, which like isn't necessarily the case for general functions. Eh, what else was I gonna say? Yeah, so like all the weights are ones and zeros. Okay, so yeah, then like this thing, like I'm gonna go to 3 dimensions, guys. This is too heavy for my bit rate on my codecs on my video. Anyway, so the matrix B is the Hamming distance, is the pairwise Hamming distance. So we have all of the inputs going down the rows, all possible inputs going down the rows, going down the columns, and we compute the Hamming distance after the mapping, the transformation encoded by matrix A, which is the parameter vector. Right. So, like for instance, like one thing that's actually kind of useful is yeah, if we turn off the animation, because that's annoying, it's like highly annoying, and we just, so this is just going to be raw Hamming distance on the inputs. So like there's not actually going to be yeah, so like matrix A doesn't actually matter. So okay, so like this is like raw Hamming distance between all of the for just 5 dimensions, and I wanted to see, would that be useful in any way? Yeah, it's actually a bit of a challenge to try to interpret what's happening. So like I have like, so let's see, we're in what, 5 dimensions? I already forgot what 5 is. No, maybe we're in, yeah, we're in 5. So we have 32 inputs, and they're arranged by like Hamming weight. So like the first row is like the all zeros vector, and the right. So like these 5 rows correspond to where you have a single 1, and so like this whole square is all vectors with Hamming weight 1, Hamming distance to every other vector, and so yeah, like they're all going to be 2 distance away because they have different ones, unless it's the vector itself, and so you have like the 0 down the middle, which, because like you have Hamming distance of 0 to itself, and then we do like the next 5 choose 2, which I think is going to be all of these, and like those range in distance. So like if they don't have, so these are strings with 5 zeros and 2 ones. So like if those 2 ones do not intersect, then the distance is going to be 4. So like, you know, you have like 3 4s, and then if they intersect on one of the ones, then you're gonna have a Hamming distance of 2. Yeah, so like it kind of I don't know how to do 5 choose 3. I guess it's this, well, yeah, it's just the inverse actually, right? So yeah, so like these 2 squares are identical to each other because 5 choose 2 is the same as 5 choose 3. That has nothing to do with neural nets. That's just binary stuff. So if we go back to actually visualizing the actual transformation, then you know we have like, yeah, I mean, it's not really right. So like we can click on the weights, and it will it'll update all of the Hamming distances, and here's a conjecture. Every Hamming distance only moves by 1. No, actually that's not true. yeah, I was trying to determine to what extent like you can like comprehend, like if I flip a bit, because like flipping a single bit seems to have like it affects every pair. Um, I mean, like there's also the issue of there's like a lot of redundancy in this matrix because like the Hamming distance doesn't depend on the order of the pairs. So you could actually just look at the top triangle, and I think there's another symmetry that I don't understand. Right. So let's also look at the delta. So it's like the exact same thing, except we're now, for the given mapping, we're visualizing the change in Hamming distance between two pairs. And yeah, I'm gonna animate that, isn't it? Yeah. I should probably, if you turn off the drawing the number, that's also kind of cool. And then, yeah, but let me go back to like 4, because 5 is pretty crazy. Maybe if you go to 3, there's like, maybe there's like a pattern you could see somehow. So anyway, these are the deltas, where I think so we're doing a random walk through the parameter space, and it's showing red cells correspond to pairs of inputs that increase Hamming distance under the transformation. I think. Yeah, actually, I kind of needed those numbers because I don't know what it's actually doing. Right, yeah, see the reds are positive. So meaning Hamming distance has increased by that amount. Let's go back to not animating. And yeah, so then we can we can toggle this one bit, and yeah. So yeah, I mean, I don't. It's kind of hard to glean any useful things, but it does suggest an idea that I was going to pursue in this video. Although, like, I was going to yeah. Let me go back to the animation. It's kind of maybe if we do like, I don't know, 350. That's a good interval. So anyway, here, like, let's adjust, like here's a way of thinking about stuff, right? So, every one of these mappings is, I mean, like there's a, because we're using binary values, there's a discrete number, there's a finite and discrete number of possible layers, right? Because for, you know, like in this case, we have 16 parameters, you know, so there's, you know, 4 times 4, so there's 2 power 16, I don't actually know, I think it's 65,000 maybe? We'll just pretend that's, well, it's like, okay, 1,000, 2,000, 4,000, 8,000, 16,000, maybe it's 32,000, I don't know. Anyway, there's that many possible transformations. And so a neural net is just a sequence of these, you know, like 30,000 different transformations. And I think moreover though, like this suggests a like a greedy way of programming a neural net. So like if you have a given I guess like target function, you could kind of say, you could interpret that as saying like all of the input strings that I want to you know, that are +1, like I want the you know, I want to map all of those strings to some, you know, like final representation, and the -1 strings to some different final representation. And in terms of pairwise distances, if those two representations are like, you know, pretty far apart, then that would be good. So it kind of seems like this idea of like you can, you know, you like, so yeah, like you can visualize the whole thing in terms of like pairwise distance matrices, right? So like you have a starting, you have a starting pairwise distance matrix, which is given by nature, you know, like by, you know, like, but anyway, and then you have like this target pairwise distance matrix, and then right, and then it's kind of like what you can do. So like you have to get from the one matrix to the other matrix, and it seems like what you could do, sorry, like I'm trying to like, I want to do a different animation. Okay, don't draw that, and go back to 5. Yeah, whoa. Anyway, so, right. Right, so like as a human programmer, you know, like what you're doing, or, you know, like one interpretation of what you're doing is, you know, you have like these 32,000 or 60,000, you know, we don't know what 2 power, actually now we're doing 2 power 25. I have no idea what 2 power 25 is. That's a very big number. Well, let's just do that real fast. Math.pow 225. Oh no, where'd it go? Oh, jeez. It's 33 million. I mean, that's just if you prefer like decimal representation of your integers. so anyway, yeah, like if you're a human programmer and you're like, I have to like program a neural net. At every step, you have 33 million choices, of like which layer you're going to lay down or use. And, right, so like 33 million choices is like too hard to like think about. But, anyway, you could just, you could imagine like randomly sampling some of those layers, and right, and so the whole idea is basically just this heuristic for if a layer is good or bad. So like a layer is good if the like for every pair of inputs that receive different outputs, the layer like increases the Hamming distance, right? So like it has like a red cell in that corresponding cell, and two inputs that receive opposite outputs. If you're you choose a layer that has a blue cell, right? Like it moves them closer together. And that's the heuristic, like that's like the whole heuristic. And so there's gonna be a couple of things where it's like, you might not be able to find a layer that like perfectly does everything you wanted to do. And it's kind of like that's fine as long as for input pairs that are distinguished, like their current representation Hamming distance can never go to 0, right? Like it always has to be greater than 0. Like that's the only like failure case. So right, so like yeah, that's like the whole idea of what we want to try to implement. I think it might be overly ambitious, but yeah, we were going to try to implement like I think like a 3JS animation, like doing that, where you have like your starting Hamming distance matrix, and then like your target Hamming distance matrix. And now the other thing is like, as you go along in the layers, the like the representations of all the points change, and like as points that receive the same input are mapped to the same representation, the number of like rows and columns that you care about shrinks, which I think possibly makes it more likely that you can find a layer that makes improvement on your current representation. Yeah, so anyway, we basically wanted to make an animation that, it looks like this, basically. And, although, also, kind of the main thing I had wanted to do was, like, understand the, like, causality between, like, toggling a parameter and what happens to all the pairwise distances. That seems pretty impossible, though. Every time you toggle a parameter, it does all sorts of stuff. Like, it's crazy. Yeah, so anyway, Right, so I think, right, so we just want to like implement this algorithm where you have a right, you're trying to achieve a particular pairwise distance matrix, like because you're saying like I have a binary function, all the plus one, it's you have plus one minus one outputs, and I want those, the inputs, I want them to be mapped to representations that for any like row column that corresponds to inputs that are separated by the function. I want that Hamming distance to be like as large as possible, which means like the yeah, and vice versa. And but I mean the other thing, of course, is that the representations will change like every layer. Yeah. So I mean, it's not really clear. This is I mean, even if you found like a solution, it's not. I mean, it probably wouldn't be interpretable, frankly. Well, yeah, I mean, like the thing that's not interpretable is like changing the representations. I mean, that was kind of the idea of this approach, though, was it's like, okay, you ignore the actual representations and you just focus on the current pairwise Hamming distances. Yeah, that might be fine. Yeah. Right. So like for the visualization, okay, yeah. So you'd have like basically every layer, you'd have two matrices. The first matrix would be your current representation as pairwise distances. So like we're somehow trying to abstract over like actual representations. Yeah, and then like below that, you would have the like the layer mapping. You would have this, which yeah, would update your so maybe you don't have to use yeah, maybe we can ignore. Does that make sense? No, that doesn't make sense. Yeah. Right, okay, so the difficulty is as you go through the network, like the representations are changing, which means that these matrices are like permuting. Well, it's like A, they're permuting, and B, they're actually like copying rows and columns. so like actually, right, like but I mean, that's probably okay. It just, it's, it's just like completely non-interpretable though. Right, because I mean, like, this pairwise distance matrix is assuming, like all the rows are like standard representation. So if I like permute the rows, then you have to permute the matrix. And also, if two rows map to the same input, then like that copies, like that row and column copies in this. Right. But that's probably fine. And then, so, right, so I mean, like the, okay, so like the algorithm would be something like, I guess it's also like your target representation will also change, because yeah, right, right. Um, yeah, so I'm not gonna be able to implement all of that in a single thing. It's kind of just like, yeah, maybe we could just play with that idea of updating the target function given like a current mapping from inputs to the current representation of each input. And then I guess also updating the thing. Yeah, that seems fine. I mean, that's not clear, but 3JS pairwise distance representation. Alright, so we will now use various AI stuff to so first of all we need like a scaffolding 3JS thingy. Okay, alright, yeah, let's plan what we're gonna do though. I think it's just like we want to maintain like an arbitrary mapping from like inputs to current layer representation, and that's just an arbitrary mapping from bit strings to bit strings. And then, yeah, I guess like if I have like a target function, um, right, I mean, like the pairwise representation of the target function is that, like if a row and a column receive the same output, then we want them to have Hamming distance of 0. If a row and a column receive different outputs, then we want them to have Hamming distance of n, where n is the embedding dimension, or the input dimension, which we keep constant throughout the layers. So that's like what you want the pairwise thing to look like. Yeah. I think, yeah, I think it's just, we want to display the layer mappings in terms of the current representation. So you're going to have like rows and columns being copied, and also like permuted. Yeah. Right. I wonder if we can just kind of keep this, like, I don't like this code because it just uses CSS or HTML elements, but, yeah, generate binary metrics, apply matrix. Yeah, I mean, like, we do need the actual parameter representation. Right. Right, so what we need is generate binary vectors. We need a concept of like the current representation of all of the input points. Like, this is not going to be interpretable. Well, that's fine though, because it'll be a cool Three.js animation, or it'll just like not work. So there's a lot of things that can happen. Yeah, I mean, I should like write out the pseudo codes, isn't it? Good, yeah. Right. So, I mean, if we just do a random neural, yeah. So like, let's just do like a random neural net, unconcerned with the function that we shall ultimately compute. isn't it? You know, it's kind of like cellular automata, you know, like this. You could kind of, you could probably map this. You could probably map this to a cellular automaton somehow. I don't really know how. Okay, so like, start with 2 power in. Oh, I gotta use, what do you call it? LaTeX. Input vectors. Right. Yes, okay, so we'll just try to visualize like a static neural net, because like the search process I think would get a little hairy. Also, as a human, yeah, because I mean, like, for a single layer, basically you want to display the parameter matrix, the current representation, pairwise distance matrix, and then the if you apply the parameter matrix to the current representation, what would be the resulting pairwise distance matrix? Right? Yeah. Yeah. So, okay. Each layer has how do you do a list? It's not doing a list for me. Doesn't matter. Each layer has, okay, like current representation, which is input vector to current rep. Why doesn't it make it a list? Huh. Do you have to do, whatever, that's fine. Everything's fine. I don't even want a list. The current representation, and then, yeah, okay, and then, pairwise distance matrix for current rep. Parameter matrix, like mapping to next wave. pairwise distance delta matrix, like given current rep and parameter matrix. Yeah. Right. Right. So, okay. So, yeah. Okay. So, a neural net is a list of parameter matrices, one for each layer, and right. Script will analyze a given neuron. So like yeah, okay, so for the current representation, initialized as the identity map. Initialized? Yeah. Compute and display the pairwise distance matrix. Yeah, okay, let's just make it easy. Let's just show the pairwise distance matrices as we go through. You know, we can elaborate later. Current representation. Pairwise distance matrix. Yeah, okay, so we're gonna get rid of all of those because that's too complicated. Like, I only have so much blood glucose in my brain, you know? Each layer has current representation, pairwise distance matrix for current representation. List of parameter matrices, one for each layer. The script will evaluate and visualize the given for the current representation. Compute and display the pairwise distance matrix. Yeah, and then update the current representation for the next layer. Um, yeah, that should be fine. That's all we want to do. We're just gonna focus on pair distance matrices and yeah. Um, right. So I think the best way, like in 3JS, right? Okay, so what else if we can get a 3JS scaffolding going, right? So like in a single HTML JS file, yeah, I might as well just give it everything, because, I mean, who cares? So, like, for each, representation is the thresholded common distance 0, 1 to each parameter vector. I'm like, yeah, okay, so like each matrix is displayed as a 3JS like square. With a canvas texture. Oh, I mean, yeah. Okay, a single HTML. A 3JS script that displays a rectangle with a like random texture with a texture that is a grid of pixels and which pixel is a random color. Certainly. Okay, is this doing this too complicatedly or not? Create canvas to draw texture. Right. Image data. That's fine. Put image data. Rotate. Cool. This might work. This might work. Oh, forgot to do the thingy. Whoops. What's the thingy? HTML. Oh no. Wait, what? Oh, okay. So it didn't work at all. That's cool. Why not? I don't think it added the canvas. Yeah, it didn't add the canvas, I think. Oh no, here it is. It created it itself. Okay. So does it add it to the... Okay, so like it never adds the canvas to the... Oh no, this is the off-screen canvas. Okay. It needs a... I'm pretty sure it needs its own, like... Yeah, like it just didn't add the canvas. Is it giving like an error? Oh, yeah, I should stop this one. Clear. Okay. Move on. Okay. Dang it, man. I don't know if you have to add the... do I have other regions? Don't see this. Really? I had another one. Okay. I know you have to add the thingy, but I don't know. Give me a single line to create a canvas for 3JS to render to. No, stop. Renderer. I mean, like, renderer. Okay, so if I do that, will that be cool? Oh. Okay, we are doing that. Is that the problem? Why is this not rendering? Well, okay, let's just rerun it. That'll be cool. So, because I think I just got confused on. Wait, how do you rerun it? I thought you could rerun the thing. Jeez, man, it's gonna take forever. Yeah, well,